Welcome back. In this video, we're going to talk about a couple different topics, but we're going to start with partial differentiation, but implicitly. So recall that difference. We could say y equals 3x squared plus 2x minus 1. So this function, y, is written explicitly in terms of x. But we might have situations where I've got 3xy squared plus the square root of y, I don't know, equals 10 minus x squared y minus the cube root of y. So in this equation, it'd be very hard, pretty hard at least, for us to isolate just x or just y and write y explicitly in terms of x or x explicitly in terms of y. So this function, we say, is defined implicitly. And so if it's implicitly defined, we just differentiate it, again, paying attention to the variable with which we are considering. And if we take the derivative of a variable which is not being considered, like we would just write dy dx. If we were differentiating y with respect to x and it wasn't being treated as a constant, we would write dy dx behind it. So we're going to do the same thing here. I want you to keep in mind, again, most of the times we call these functions z as a function in terms of x and y. Okay, so when I differentiate this function, I'm going to treat y as a constant. And when I take the derivative of z with respect to x, I'm going to write dz dx behind it. All right, so z is a function of two independent variables of x and y, and we're going to differentiate both sides with respect to x. So when I'm teaching this in Calc 1, I always write out all my terms. So I'm going to take partial with respect to x of yz minus partial with respect to x of natural log of z equals partial with respect to x of x, and then plus partial with respect to x of y. So remember, y is constant. Z is my dependent variable. So y is constant, z is the dependent variable. So if this was a constant like 3z and I took the derivative, I would just get that coefficient 3. So here I'm going to get the coefficient y. However, I took the derivative of z with respect to x. So let's do that again. If I'm differentiating ln z, the derivative of natural log z is 1 over z. And again, I took the derivative of the dependent variable, so I'm going to write dz dx. The derivative with respect to x of x is 1. Oops, I need to write my pen there. And the derivative with respect to x of a constant, right here, that's going to be 0. So factoring on the left, I can factor out dz dx. That leaves me with y minus 1 over z, and the right simplifies to 1. So dz dx is 1 over y minus 1 over z. And cleaning that up, multiplying by the LCD, that's z over zy minus 1. So implicit differentiation works the same way. You just need to consider which variable is independent, which one is dependent, right? Which one's your x independent, and which one's your y or f of x, the dependent variable. And then what variable is going to be a constant. All right, let's look at another example. For this example, we're dealing with a paraboloid. Z equals x squared plus y squared. And we have a plane, x equals 1, intersecting this paraboloid and creating a parabola, right? So we want to find the slope of the tangent to the parabola at this point. So running along that parabola, running along that plane where x equals 1. So in this problem, since we're going along the parabola at x equals 1, we're going to use x equals 1. That will be my constant. So I'm going to treat it as a constant as I work through the problem. But I'm not going to plug any numbers in until the very end. So, and if x is a constant, that means y is my independent variable, z is my dependent variable. So I want to differentiate with respect to y. So we're going to find the partial with respect to y of this function. Z equals x squared plus y squared. So that tells us the partial of z with respect to y. The derivative of x squared is 0, and the derivative of y squared is 2y. 0 plus 2y tells me my partial is 2y. So this formula gives me the slope of the tangent given any point where x is equal to 1 on that parabola. So in this case, when we go to find the slope at that point in the plane x equals 1, dz dy at 1, 2, 5, that's going to equal 2 times my y value 2, or 4. 4 represents the slope of the tangent line at that point. And I have a picture to pull in, and we also have a check that we're going to talk about. So we started with this surface, this paraboloid. We sliced it with the plane at x equals 1. And what that did was create this parabolic curve along the surface. So at any x equals 1 that's on that surface, it's going to be on that parabola. So we're looking at this specific point, and the slope of the tangent line, which is in that same plane, running parallel to the parabola in that plane, that slope is 4. So visually, that's what we just did, and we have a check that we can use. Our check method is to treat the parabola, I forget how to spell words, as the graph of a single variable function. So thinking about that, z equals x squared plus y squared. In this case, if it was 1, that would be 1 squared plus y squared. Z equals 1 plus y squared. Again, differentiating the derivative. In that case, it wouldn't need to be partial. We'd say the derivative of z with respect to y is 0 plus 2y. And we would again just evaluate that at 2y. Okay, so I hope that helps. We're going to do one more example in this video. For our third example in this video, we're going to talk about functions with more than 2 variables. So maybe we have w in terms of x, y, and z. We have 3 independent variables. And all we have to do are hold the other independent variables, whichever one's not being differentiated with respect to any of the other ones would be constants. So in this case, we're being asked to differentiate w partially with respect to z. And this could also be written as the partial of f with respect to z, because f means the function w, right? That means the same thing, it's just a different notation. So I just wanted to point that out. Okay, so if we're differentiating with respect to z, z is my variable. That means y and x are constants. So in the video before this, I worked it out and I used the product rule, but do we really need to use the product rule here? If x is a constant, I don't, because whatever I do for my second piece of the product rule, the derivative of x, derivative of that constant is going to be 0. So we don't have to use the product rule. Partial of w with respect to x is x, taking the derivative of sine. That is cosine of the argument y plus 3z. However, we are not done. We have to use the chain rule. So the partial with respect to, I wrote x, I always do that. The partial with respect to z of that argument, which is y plus 3z. And I'm sure you guys do that too. You get in the habit of always doing things in terms of x, and then you write x's, especially when you're using different variables like theta and r. You're going to write your answer in terms of x because you're just used to thinking of it that way. But always paying attention to your work. So we're differentiating with respect to z. We took the derivative of this, treating x as a constant. The derivative of sine is cosine. The constant would just remain in front. And then we have to take the derivative of the argument using the chain rule. So y is a constant, and the derivative of a constant is 0. The derivative of 3z, since we are differentiating partially with respect to z, that's going to give us a 3. So this turns into 0 plus 3, which is 3. So the partial of w with respect to z is 3x times the cosine of y plus 3z. Final answer. So I hope that helps you understand what's going on a little bit better. As always, please send me an email if you have questions. Use that handy Ask My Instructor a question button. That's the best way, because then I know exactly what problem you're looking at. All right, hang in there, have fun.